In this tutorial we are going to learn to model and analyze a simple aircraft wing with two control surfaces. We start by creating a new project and going to the Model tab. Let's create the wing by clicking the Aerodynamic Surface button. In this dialog box, we have several parameters and options available to define the surface. Starting with the title. Let us put in wing as the title of our surface. For now, we will keep other parameters such as the root chord length and its offset, tip chord length, mesh density, and wingspan as default values. And select mirrored option as the shape of the wing. Let's click on Preview to view the wing in the workspace. Now, we'll change the tip chord length, its X offset, and the half span value. And preview the model. Add to Workspace button creates the surface and adds it to the workspace tree on the left. We can rotate the model through A and D keys on the keyboard, or use one of the preset views from the View tab. We can also display or hide the surface title and coordinate systems. Next, we switch on the panel IDs to view the ID numbers assigned to the newly created panels. Now, we go back to the Model tab and click on Control Surface Modeling option. This dialog box allows us to define a control surface over the wing by assigning the panel numbers. Let's call this control surface Aileron 1. Now we shall assign 8 panels from the trailing edge of the port side of the wing. We can create a similar control surface on the starboard side of the wing as well. Let's call this Aileron 2 and assign 8 panels to it from the trailing edge of the other side of the wing. This creates 2 control surfaces with their dedicated coordinate systems. These coordinate systems can be used to deflect the control surfaces for aerodynamic analysis. Next, we are going to conduct a steady-state aerodynamic analysis of this wing. Starting with going to the Input tab and creating a geometric input set. In this dialog box, we can define aerodynamic reference parameters to be used for analysis. We start by naming the input set. Let's call it Input 1. Then we define the reference chord length, half span length, and reference area. The input set is now visible in the workspace tree. Next, we need to define a CG reference point for aerodynamic moments calculations. We can do so by creating a structural mass stiffness element from the Model tab. We will name it CG and click Create. For this analysis we need the aircraft CG to be at wing tip, so we can define the length of the stiffness element accordingly. We can see this structural element in the workspace tree. Now by right-clicking on it we can calculate the aircraft's CG. Once the geometric inputs and CG are defined we can proceed to analysis. For a quick steady-state aerodynamic analysis we go to the Analysis tab and select the Single Analysis option. In this dialog box we can give this analysis a title and choose a reference CG if we have created more than one. Then we can set up our analysis with parameters such as the aircraft's airspeed, angle of attack, side slip angle, roll pitch yaw angles and rates, as well as flight altitude and Mach number. Finally we select the geometric parameters input set that we created earlier. For now we will leave the control surfaces undeflected and click Solve. We can immediately see the pressure distribution over the wing, with a pressure coefficient legend on the right side of the screen. On the left we can see the input parameters in the top column, and results in the bottom column. The results calculated for this analysis are the lift and drag coefficients, calculated in the wind axis, and three force coefficients Cx, Cy, and Cz, calculated in the body axis, and the three moment coefficients for roll, pitch, and yaw moments, denoted by Cl, Cm, and Cn. We can also view the lift and drag force distribution over the wing by selecting the options from the View tab. The analysis is now saved and visible in the solution tree. We will now deflect one of the control surfaces and analyze its effect on the lift distribution. Let us deflect aileron 1 by 20 degrees. We can now see that both lift and drag is increased on the port side of the wing. The actual lift force values can also be seen on the plot.